okay, now we want to do optimization, all right? And then for that, then I brought in the minimize, basically function from sum. So that's sort of what I'm bringing. All right, well, let's go on. So we need then a function to do the minimization. So I define a function which is a function of x, all right? There is a function of two components. So W1 is the first component, and W2 is the second component of this x. So that's a bivariate function, all right? Then I have R, F, so these are the guys. So maybe I take them inside the function. So that's self-contained. So these are the stuff. Now, the function that we have has a numerator. It's called a num. And numerator is, W1, these are the numerator now. That is what we have. For any rating scheme, then we have a numerator, and then we have also a denominator. Sorry, when you were not here, then I said that you bring this function to do the minimization. So that's the minimize from SciPy. Alright. And we do a function so that we can do the minimization. Right? Now, this function should return the numerator divided by the denominator. Because we are doing a minimization, but our problem is a maximization, and we multiply by minus. So, when you do the optimization, you need also to say what is the space, the search space. Well, so to speak, what are W's that we can, because that's numerical. And we need constraints. So here we have constraints, let's call it constraint 1 as a function of x, and that is W1 is x0, W2 is x1. That's W2. Alright. And then we want that it returns 1 minus W1 minus W2. Right? So obviously we want this constraint to hold. Right? So that should be 1 minus the value of this function should be 0. And all of the values of x. Right? That's 1. Well, that's another one. Yeah. But then we also have bounds. So W1 and W2, both of them should be, if the summation is 1 and then they are positive, then they should be between 0 and 1. Right? So that's sort of what we have. So then every variable then has a bound. We'll generate the bounds too. So the first one has a bound, but we pass it as a tuple, right? Like so. So that is the bound for the first variable, and that is the bound for the second. Right? So these are the bounds that we have, and then we put them together as that becomes a nested tuple. Right? So that's important that they are tuples. So we print this. Not lists, they're tuples. And that's nested. So that's the first one is for the first tuple, and that is the other one. So they come together. Well, because that's numerical optimization, then we need somehow some starting point. Right? So we can go on with the minimization. Right? So, let's call it x0 or w0. Well, here we pass it as an array. Right? So we basically define an array of, let's say, 0.4 and 0.6. Right? So that's one starting point. Right? So the starting point is a feasible one. Feasible in the sense that the sum is 1. So this concept constraint is satisfied. Right? But if you don't have if there is no constraint, then you don't need to care about starting with a feasible solution, but that's a feasible. So that is what we have. Right? So now we have to put together, well, I mean, these constraints somehow together. Right? So let's focus on const 1. So the constraint number 1. Right? So I call it like so, and then I pass it as a dictionary. Look, I mean, this is stuff that I'm telling you, you know. Right? I've worked with optimize before. So you understand the tuple form and then the dictionary and so on and so forth. So you can do optimization. That is what I'm saying. Okay. Let me ask this question more clearly. What type of optimization did you do in Python? What did you optimize in Python? What type of exercises you did?
Just follow the code of the actual, how to actually exercise the optimize.
Alright, so the question is more, you did unconstrained optimization or only constrained or both?
Like, not with this thing.
Okay. It doesn't matter. Then I will, so that's good. Then I actually explain all the details I'm doing. So, that's right. Well, so the constraint number 1, which is this function, is a constraint that should hold. Alright? So that's an equality constraint. So then we say that, look, I mean, the function that we have here, its type is EQ. EQ stands for equality. So then the function later will understand that this is a value when there is a function, and the function we have defined as cons 1. Right? So that's constraint number 1. It's a function, and this is how we pass it to the minimize. Right? We say this is an equality of this function, which is defined out there as cons 1. Right? So that should always be an equality. Right? It's a function. To 0. Right? So equality means that it's equal to 0. Okay? So now we are more or less ready to go on and then pass everything to this function. Well, let's call it results. That's the usual container. And then we call the minimize function. And then asks us, okay, what is the function you want to minimize? The function is called f. Right? So that is what we have. And then says, okay, where do you want to start from? We say we start from x0. Alright, so that is the starting point. Well, I mean, there are different ways of doing the optimization, of course, right? So you have the quadratures, you have the simple Newton-Raphson, sort of different basically methods that we have. Right? I mean, one method which sort of seems to be okay, so that's a quadrature, it's called SLS. So that's a QP, so that's a quadratic, well, I mean, it's a quadratic function, so polynomial, alright? Which sort of, at each point then linearizes the function, looks at the quadratic optimization, quadratic basically fit at every point, points sort of, so locally looks at the function as quadratic, and then goes sort of to find the optimum. And now we have to also find sort of then there are some bounds, and these bounds we defined it as bounds as a tuple, so that's another one. And then we have a constraint, and the constraint, which is a dictionary, we pass it as a list. Alright, so because you may have core constraints, and you have non-linear ones, and so on and so forth. Right? So these consts, which we have defined as a dictionary, may have other constraints. Right? Other constraints on the base. So, well, I mean, now that we are here, then we can indeed pass this, or sort of let it run, and then the results will indeed include a property which is called x, and that will be the optimum value. you have this.
Yeah.
And you printed the result. So this is the value of the function. You have the where is the x? Yes, so it's 0.44%. 44% you put in the first asset, 56% you put in the second. But of course you could do this by hand, right? Do the first order condition and so on and so forth. But let's say somebody comes and then says, look, I want at least 50% or 60% in the first asset. Yeah, so that becomes a constraint optimization. So to speak, I want at least 60% in the first. Don't give me this. Right? So then we can indeed go on in the first asset and then change the bound. Right? So it starts from 0.6 and then goes on. Right? Or you can change the constraints as you want, as you please. Right? And then run it again. Then we get 0.6, that's the minimum, so the maximum. 0.6 and 0.4. If somebody, say you have a client wants at least 60% in the first asset, then you do that. And of course for every, whatever, so if I don't have it, yeah, so 0.6, then here we have, well that's the optimum, without any, that will be the best utility that you can get, or the best sharp ratio, so to speak. Right? So that's sort of what we have here. Good. Well, let's maybe calculate here. All right. So here we have W1 opt. All right. So that's the optimal weight, which is results dot x, the first value, and results dot x, the second one becomes the W2, the optimal value. All right. And then let's say you want to calculate, say, the optimal risk and the excess return. All right, so that becomes actually very easy. You can say print for me, or let's take this, two, the numerator and denominator, and, well, calculate. Okay, so let's calculate the numerator. So that will be times opt1. W1 opt1, and W2 opt2 minus the risk-free rate. So that will be the risk that we have for, sorry, the return of the optimal portfolio. And this is opt. Look at them. Alright, so undefined, of course they are not. So that is what we have. Like 14.9, so almost 15. Right. And that is the risk, risk-free, that is the optimal rate minus the risk-free rate. So, that will be like 12%. It's sort of this portfolio will pay us. 12 and 15 or so will be the optimal value for the standard deviation. Right. Good. But this step is always important. And you in the end say, all right, I did the optimization, then what is the return that I get, and what is the standard deviation? Right. So that's sort of always nice to take a look at. But how much does my portfolio bring on average? Right. So that was just to get you going. Alright, so this is the optimal risky portfolio. Alright. Well, then there is also an optimal finite portfolio. Alright, so OFP, which is indeed sort of says, okay, so let's say we have some funds, portfolio together, which is sort of a little bit better, maybe. So by including also a bit of risk-free rate. Another thing, we have a fraction, P, and then 1 minus P of our funds. All of the funds that we have, let's say, are F. Right? And let's say we break it into 2 pieces. All right, so half, say, let's say I have 10,000. 10,000 euros. Right? And I say, well, a fraction P, I invest in risky portfolio. So now let's say P prime to be 0.7, and then this is 4%. Then I calculate 7,000. Right? And then I have 2 assets. Asset 1 and asset 2. Right? So here we based on these returns and so on and so forth, then when the weight here turned out to be roughly 44, and then the W turned out to be 56. So these are break into 2 pieces. How much I put in here? So 44% I put in asset 1, 56% I put in asset. Now I still have 3,000 left. So this 3,000 euros, then you will spend in the risk-free rate, buying the bonds. Yeah. By doing this, what you do is that you reduce the risk. Right? Well, the closer this one is to, well, this is a risky portfolio, both are risky. This is riskless. That's a risk-free rate. RF. So if I actually break this fund into these pieces, one piece becomes that, and then the other fully goes into risk-free rate, then I will be reducing the risk. Right? So if, well, that's a risky asset portfolio, and this is a risk-free rate, then we have a second indeed a step of breaking the funds or finding weights, such that we could reduce the risk. Right? And that is something that moves us along that red line. Right? So the red, the blue, and the red meet, right, is if I invest in that, it means I don't want any of the risk-free rate. Okay? That will be a fully asset invest in the others. But if I want to invest in the risk-free rate, then I move along the red line. The bigger, well, the P, the closer I am to the tangent line, the smaller, then I'm closer to the risk-free rate. Right? So if this is 0, then I'm really fully invested in that. So that gives you a hand in reducing the risk of the portfolio. Of course, it reduces the return. Right? The return is reduced. Right? So from whatever value it is, it was like 20% or so that is there. So the return is reduced because you move along this line, but also the standard deviation, which is the risk. Can I have my book here?
So, just to, thank you very much.
So, I will give you. Good. I will give you so that you have it. Look at it. All right. And we have a second indeed dimension. Right? So here we say the final portfolio that we put together, then it has returns. That will be the optimal final portfolio returns. Then it gives us P% from the optimal risky portfolio, ORP, and plus 1 minus P of the risk-free rate. So that will be the returns of the optimal final portfolio. So when you calculate the variance of this, of course you can. Right? So that will be, well, this is equal to, well, the variance, let's calculate the variance of the optimal final portfolio. Right? So let's look at that. So that will be the variance of this. But this is risk-free, so it doesn't actually contribute to the variance, so that will drop. fraction right, p squared times the variance of the optimum risky portfolio.
Well, this is a standard deviation.
Well, to the power of 2, that would be 15 to the power of, that's 225. Right? So that is what we have. I mean, for this exercise, that is what we have. Now we want to find p. Right? But let's put together a utility function. A utility function, which is a function of p, and of course, for all of those quantities. The return of optimal risky portfolio, so the expected value, say, and the variance. I can actually write it like mu of ORP, that's the expected value, and the variance of ORP. Alright, so let's basically put together this portfolio. This utility function. That's the second step utility function. So that will be essentially the return you have that you get from the optimal risky portfolio. Right? Which is this, so there is p times r of ORP plus the return that you get from the other one minus this RF, so that is what we have. And now we have to subtract the variance. The variance, that's the reason. So we have to subtract. So when here things are different, the book that I have uses this function times some alpha, which is a risk aversion parameter. So that is what we have. So that's the risk aversion parameter times sigma squared of ORP. So times p squared. So that becomes a utility function. This alpha is a risk aversion parameter. So the book actually says that you choose alpha a number between 2 and 5. So the suggested values. Suggestion for alpha is a number between 5 and 2. So if it is 5, then you have more risk aversion. So risk is punished more. So you don't want to have so much. If you say 2, then you have the minimum value. So we have in this case. You can change this to your own taste and appetite. But that is what we have. And then if you do the, well, that's for the quadratic function, you can take it as the very first of the condition with respect to p, and then for the p star will be the expected value of the ORP. Right? So that will be the mu of ORP. Right? Minus the risk-free rate divided by 0.1, so that's gives us quadratic. You take it away, becomes 2 minus 5 becomes 0.1 times alpha and sigma squared of ORP. So that becomes the, that's a very simple treatment. Right? Alright, and then you tell me what fraction I put in the risky asset and what fraction I put in the riskless. So that becomes the optimal final portfolio. Right? Which, as I said, it moves us along this red line. So we move down, we move towards the risk-free, totally in the risk-free. So that would be some number that we have. All right. Well, that was a little bit of very simple example, no real data. All right. And well, let's now go and start doing some analysis with real data. And I want to do real data stuff by hand. Though we can, because that's the theory. It's very easy. You pass everything that's optimized, and so on and so forth, but it will give you a package, right? So a package which is very strong when it comes to such type of tasks, right? So alright, let's then go on. I want to save this so it doesn't go anywhere. Let's do it here. Let's do it there. Alright, so let's ignore. So let's MDT. Numerical example. And we are in day 7, right? That's our day 7 of the class. Alright. Let's go on. Alright. Move ahead. We're doing, well, essentially real data. Alright. And the data you have, right? So we have to indeed go and then get them and so on and so forth. So that is what we do. But the package that we have is called RISC-FOIL library. That's actually a nice library. Sometimes it helps, and then the descriptions are written in Spanish, because the person who developed that is a Spanish. So it doesn't matter. But sometimes they also in English, that's not a problem. Right? So, well, please install it. Alright, so let's look at the installation. Well, I mean, you have to install it. I don't know, now we have Windows and the Macs and so on and so forth, so that could be a little problematic. So what you do is try this. Alright. So click install RISC-FOIL-lib. Right. So that is to do all this stuff that we did. So rather using this package, I will tell you how it works. We'll do some exercises with that. So and I want to know if it works. So if it's working, it will take some time. You may need to sort of install Visual Studio, I don't know. I always forget. I should write something on this board. Put the microphone on. Doesn't work. You didn't install it. Alright, so once you have it, then you can go on and then do some stuff there. And the guy also put together, that's a book, I didn't know. And how much is it? Oh, 85. And the book is new. Right, so, well, I mean, the person who wrote this also put together a book, just to sort of see how to use this. What did I tell you? Right. I will tell you the beginning of it. And I will tell you also what functions it is, how you can play around with it. So you get simple, sort of get nice results out of this. But if you want to do more, then you have to dig more. But it's a Mac.
can you do a, so can you do a pip list? Pip list? So we need to look at fuzzy TM. So let's do pip freeze, everybody finish. For you it worked. Well, okay. Oh, that's good. So let's look at fuzzy. Where's JC? So what did you want? So you wanted some packages. Where is this? Fuzzy TM, which is not installed. So can you install fuzzy TM? Pip install fuzzy. What is it? What does it do? What does it do? So you need to know a newer lambda. Lambda lambda. Let's do this again, or pip freeze. That's always somehow behind it. I want to know if you have this bind package. But everybody else was successful in installing. Are you? What?
Just stage setup.
Oh, let's restart. So it doesn't say which we need. Let's look at. I think maybe I don't know what is the problem with your laptop or sort of with your installation. Do you have Python as a standalone or is it from Anacron? So that's sort of what and maybe this is what you should follow in the steps that it tells us. Right, so Python you have, I just saw. You have to now check if you have this. And then there is the CDX Pi. Right, so you have to see if you have this. already there. Okay. Almost there, so successful. Again, any problem? I'm sorry, I don't know how to solve this. Right, so you oftentimes have problems with Macs and classes, not often, now and then. Maybe you program with her. But what you could also do is maybe go away from Spider for this. It depends what you want to do. Right? So later, if you want to use this, then maybe you install some other item. Right? So not the Spider, maybe you use PyCharm as here uses. So it's sort of more professional stuff. Right? And but I don't really know. So, let's go on with sort of, so if you have it, I don't know if I have it, but let's start doing some visual analysis. So let's say we have NumPy as NP, so that is what I generally do. Let's import pandas as PD because we do have some data we want to basically analyze, manipulate, and so on and so forth. So here we import riskfolio as risk RP. Let me see if I have it myself. Seems I did. I installed it some time ago. Okay. And let's import the matplotlib and so on and so forth. But maybe before I go on, so I will go and then take, you remember, so we did form of French, right? So that was daily and stuff, right? Well, we could do monthly data, right? Where the frequency is a little bit different, so I will go ahead and take daily ones, right? So we have more data and then we can do more stuff, right? So more flexible in terms of data points. I feel so bad for you. Now I can't teach. Unless it's on my. You can do it. Alright, so let's take data that we have from the farmer French, right? That we did the other day. Then we calculated the returns, and then we merged the data, and then we put stuff, right? So we just go and then take those. Alright, so here from the farmer French day 6, alright, so I'm taking the first lines up to the merged data. Alright. Because there is also risk-free rate and so on and so forth, so that is what we basically can use. Okay. I will just run it, and I have the log difference data. So all of this fine and run. So you understood what did I do? I went to the farmer French of yesterday, alright, and then took the first part where we have the returns. So you have the farmer French. I want the farmer French data because you will see why. Alright, so that will help us with the variance estimation. So that part I took, went to the other basically file, and then we can do some analysis with it. Alright. So these are the merged data that we have. Alright. And well, let's just start with a simple exercise, and then we take two assets. Maybe I should wait so that we do things.
You're fine, you can go on.
I cannot understand this value.
You also have the copy. What does it say? So, do you have Visual Studio on your machine?
Yeah, that's good.
That is already there. You have to play around with it so that you can install. I don't know. But you have to really sit down and then review what's going on, but maybe you also look at tools. So that you can go. But the rest are good. So that's good. But let's take two assets. I mean, let's see what assets do we have. So we go to my data, open the file, and well, I mean, I can actually, so here we have the returns. Okay, this is what I need. Let's go invest in, where is Amazon? Alright, so that's Amazon. Can we take Amazon? Oh, very risky. So that's AMZN. So equity. Alright, so that is number one. And what is the Apple? Haha. APL. So that's an ongoing equity. Alright, so these are the assets. I just take two, okay? So simple. Simple basically stuff. Alright, so these are the two assets I want to invest in. Alright. Now let's get the returns. So that will be from the merge data, I will go read assets. And that will be what I want to work with. That's it. Right? So this is my red, which has two columns, Amazon and Apple. Right? So these are the two assets we want to go invest in. So, well, I mean, if you are successful in putting together this portfolio, then you can define a portfolio with it. So that's a model again. So let's call it R4. That will be from RP. Then we bring in a function or a method which is called portfolio. Alright. And the portfolio, well, takes a lot of inputs. Alright. Alright. Well, the first one is the returns. Well, and then there are many other basic variables, which fine-tune the utility function. So, sort of the utility function that we had in the beginning was Sharpe ratio, right? And then there are some stuff that one can bring in, some weights, some sort of bounds, and so on and so forth, right? So we stay with the simplest, first with the simplest basically form. And we say that the returns that I want to basically go invest in are in this basically data frame which is called the PRET. Right, so that's the portfolio. It generates sort of the raw portfolio, and then we can go on and then, that is a wrapper essentially. So sort of with all of the properties that we have. Alright. Then we can play around with these a little bit. Alright. So, okay, let's just start with sort of going on and then say, how do I want, because there are the main inputs that we have in the very simple setup is the mean and the variance, both of them. I need so that I can go on and do the optimization as we did before. Right? So I need the mean and the variance. So here, well, I mean, let's just start with the simplest of the setup, and then they say that the method I want to use to calculate the
calculate the historical mean, right? So this you can change and then sort of do it a user-based. For example, you can do rolling mean. You can estimate whatever model for this means and then plug in the values the later we have. Right? And we also have the method we need for the covariance matrix. For simplicity, for now, we say that is also historical. Right? So it will use all of the historical data to do the calculation of the mean and calculation of the variance covariance method. So this becomes a sample covariance sample mean. Okay? But as I said, when the number of acids become bigger, then we have to play around with that. Right. That's all right. Now we have to go to this part which we have generated, and then go to the part which is called acid statistics, and then set the method for calculation of the mean, which is historical. This is what we have set. Method mean. Alright, so that's one thing. And then we have to also pass to this the covariance method. How do you want to calculate the covariance method, which is method code. So they're both historical. Just do it like that so that it's very clean, and then you understand so what do we do step by step. That is the two things that we have in the very beginning. So now we do some basically parameters that we have here. Right? So let's just start with the model. So we basically start with the model and passing to this classic. Right? Classic is the classical model portfolio theory stuff, as we just saw. Right? So under the assumptions that we made, and so on and so forth. So the risk method, sort of, you have the risk as a function of variance. So we measure the risk as a variance, right? Now we have to say, all right, so what is the model sort of that we have here? We say that this is mean variance. Right? So that's the sort of mean variance and stuff. And then we define what is the, well, there's the mean variance, so that mean is good, variance is bad. And the objective function we have to also pass. We say this is sharp. Alright, so that will be the risk adjusted excess regard. That will be the objective function. So that's the sharp, that's the objective function. We have to also pass it. Alright. So, well, we need to pass a risk-free rate. Alright. Well, let's take 3%. Alright. Well, that's yearly or daily, I don't know. I mean, sort of, let's say that this is a yearly basically rate. Alright. Then we have to divide it by 12 so that it is roughly from yearly becomes monthly, and then we divide it by 22 so that we have daily. So that's actually very small. Alright. And then there is also a risk aversion parameter which I set it to 0. Alright. Well, that is for later. Right? So here the objective function that we have is sharp. Alright, wipe it off. So we have the sharp ratio, right? But we can actually take the utility function and change it pretty quickly. Alright, so that's a parameter which is called L. For now it's 0 because well, the objective function is the classical utility function that we have. Alright. So now that we are here, then we can actually go on and then do the optimization. Right? So we can, as you know, we can do it by hand, but also, well, I mean, we can go and then say, look, this port that we have, do the optimization for me, all right? Where the model is classic, that's the model. Rm is Rm, so we have a mean variance. The objective function is the object, as we have defined up there, so that is the sharp ratio. Set L to 0. And then we also have the risk-free rate. So we have to pass it. Let's call it this is RF. So that's the value that we have there. And then the historical method is indeed hist. turn on this, so the east is true. Right? So then we use the historical values for the calculation.
So here, well, these are true or false, and this is turned into true. Alright. So what this function actually does is it goes, puts together the Sharpe ratio, does the estimation. With the constraints between 0 and 1, the summation is 1 of the weights.
And then you are good to go. Right? So here, well, let's print W, just to see how much should be invested in. And that is the case.
So it says, okay, 30% put in Amazon, 70% put in Apple. Okay? Let's see. Okay. And we can actually tweak this a little.
Then before tweaking, we can do some visualization of this stuff. So somehow, oftentimes when you have many assets, well, of course the numbers matter, but if you want to put together somehow some portfolio and then you want people to know what it is, then you can indeed sort of do some visualization. Let's actually do pie chart. Alright, so here we have lot pie. So create a pie chart with portfolio weights. Alright, so that's a nice flow. Here we see the W's are W's. Let's have the title to the graph. And then we say that these are the Sharpe weights. The Sharpe W, or the Sharpe mean variance in the model. So that's the title of the graph. Let me just do this. I will tell you what they mean. So here we have a parameter which is called others. Alright.
Well, in here, this others doesn't matter. Alright, but because here we have two assets, 30 and 70%. Alright. But if I say 100, alright, 100 assets, then say 10 of them would have gotten the majority of the weights. The 90 will accumulatively maybe get 4%. Alright. So these will be bundled together because they are very small as others. Alright. So that is this 5% weight. So 5% bundles the lowest, basically from ranks them from the smallest to largest. Sums, whenever it is sort of 5%, all of them, cumulatively then calls them others, and then puts them on the chart. And here it doesn't matter because none of them is a small.
So that's number one. So here, when you plot them, right, so then you want to know which weight is which. All right, so if you have, say, many, all right, then the number of rows you can set to some number. So that will be on the legend. So how many assets can go on them. So if you have many assets, then they become important. So well here, well, the default is 25. Let's set it to 20 for the fun of it. All right. And well, let's actually also bring in a color map. All right. I use tab 20. All right. So that's a table of 20 different colors, right, from the matplotlib. Right. So if you have, say, 21 assets, then the first 20 will have some colors, and asset number 21 will have the color as the first. So it repeats. There are more. We can actually, but I just use tab 20. Here it doesn't matter. Well, I mean, if you want to know what they are, then let's say color maps matplotlib. Alright, so let's go to the page, and then sort of there should be something here. Alright, so that is, what they are.
can put it on a, well, if you have a previous plot, then you can, well, put that plot on that, this plot on a certain subplot. So you can put the axe, so it goes, you know, many plots and it will go and then sit there. But here we don't have. And then we say PAT coach. Okay, so these were some of options. Okay, I do not the map locally. Import map locally. Dot plot as PLT. And figure dot range, we set it to 600, right? That is what I need. And now we can plot. We get this plot.
Alright, that is the portfolio. It's a very nice visualization. We could do it on our own, but well, there is a package. So here, well, we put more funds in Apple, in new, we put 70%, but then 30% we put in the Amazon. What's a visualization? One visualization, so you know, right, so varies what.
Well, of course you can save it and so on and so forth. But let's also plot the efficient frontier. Right? So remember, we can calculate the efficient frontier, but here we can do two. Right? So if I want to do that, so let's say efficient frontier. Alright, so let's plot that. I mean, well, let me wait.
You have this plot. This looks like more like a workshop rather than a course. Sort of.
Boot camp. It's a boot camp, it's a training boot camp.
Yeah, because you're trying things out there. But the point is that you can use them. So. But of course, you can always go and read these, but then, well, I mean, hopefully you remember them. Today, then I tell you what are these options and so on. Because these are the important ones. There are many. I picked those that are interesting. Alright, so we can play around. Let's do the efficient frontier. Alright. If we wanted to do the efficient frontier, if you remember, with this exercise, then I defined some W's, some bases. So then they were 1,000 bases, and they were all dots, and so on and so forth. So that they were connected here. Right? So we have to say for this efficient frontier how many
Points
points
you need. Alright, so the number of points, let's set to 50. Don't need 50. And now we can define the frontier. Alright, so that's the frontier we want to define, and that is equal to port. There is a function which is called efficient frontier. And then this efficient frontier takes some input. So the first thing is the model, which we have defined up there. Alright, so that is number one. Well, I mean, what is the risk measure? That is mean variance. So that is what we have there. Points is equal to points. That is 50. Right? Well, needs the risk-free rate, so it can calculate essentially the frontier essentially here, right? And then the historical data returned true, alright, so which is equal to this, that is true. Now we can, well, do some beautification. Let's have a label, and then, well, I mean, it's efficient frontier, let's call it, alright. calculating the weights with W1 times the return of the first, plus W. We need the mean and the variance here. And this we have. Because when we did the optimization with the port optimize, then this port actually as an object includes a method which is called mu, so we call it port mu. And then here we also have a port code. Alright, so that's the covariance. And then we also need the values of the returns. Let's call it ret for efficient frontier, and that will be port dot returns. I just take the returns. Sort of the stuff that we have used for the optimization. So we get the returns back. We could also set them from our data, but that is the stuff that we have. Now we can go and then plot. So we calculate the frontier. Now we put together a plot. So it's called another plot. But there are actually a lot of plots. Here, so plot from here. Alright, so that is what I need. And then it says, okay, what are the weights? So W is for the frontier. And so, well, here we say that this is the frontier itself. So that is what we calculated up there. Because it does calculate the returns. There. Alright, so it says, okay, what are the returns? And we want to do some calculations with, and these are the returns. We should pass the mu. We should pass the covariance. We should pass everything. So RM, we should pass the risk-free rate, some alpha, so that is that's the opacity for some of the points. Alright, so that's sort of for beautification. Let's use a map for colors. Alright. This I've chosen. And for this one. So what are the weights? Use the weights. Did I get the weights somewhere? Right. So these are the weights. You have to pass them here. Let's see. So we add the label, which is the label. So that's the efficient frontier I called it. Let's add a marker. So for the optimal point, there will be a star. So that's the optimal point that we have. Optimality on the efficient frontier. Then there is one point which is optimal. So you want to know what it is. We can fix the size of this. We can set the color. This nice point should be red. Let's add a height of 6, a width of 10, plus the size of the graph. And there is no axis. And clear the dot. Maripol, they finish. Alright.
So I mean, so once you're done, then you run it for some this, once we write it and then later, then we just copy paste it. Oh, if you need some other functions up there, then I'm sure. You're done? And you have the frontier, you saw it?
Yeah, that's a good one. Yeah, so it should be
you have to pass the returns to ret EF. This is the problem. So returns equal ret EF. So these are the returns that we specifically use for our calculation. You have deleted everything. Maybe you Control Z and then go back.
So she shut her down.
It doesn't work.
Yes, she can go up a little bit.
How big? How big? Little bit.
Like this. At the point, people think. I don't know that, huh?
Never mind.
But this is just visualization. A lot of the stuff we do is about visualization, right? So, the package actually does a good job with this. Knowing that is. Let me also, I want to know if it works. So then if I have an error, then I can add them. Right, so. I mean, these returns are multiplied by 100, right? Like, it shouldn't, actually. So because I did the multiplication by 100, if you remember, maybe we should redo this in the calculation. So it does the multiplication again by 100. Right? So you have to divide this by 100, right? So it's not 1,900, rather 19%. So 19%, this is what we get. Below the 25% of you. Right? So because you said that you earned 25%.
No.
5?
Oh. 25.
Total 25. So that is what we have. Right? 19. So they are Apple and Amazon. They are very risky, of course, right? But then their returns is also high. So the standard deviation, we also should divide by 100, so that will be 26%, which is very, alright. 26% with a mean of 20%, that's actually pretty large. The risk-free rate is pretty low, it's almost zero. So it doesn't make sense to do the ultimate final because it's so low. So do you need my support? Should I come to your laptops? Maybe I can do something. You don't? Maybe the returns we divide by 100 so that these plots are better. And you're good, maybe? Alright, so you're also done with this section. In the next one, so I just wanted to get a hand for some working programs with two assets and then we could see them and so on and so forth. In the next section, then we will increase the number of assets. We use 50, 30, more. Alright. And then that brings challenges. These challenges we have to understand and then see how can we overcome. So some methods the challenges I will tell you, and then I will tell you how to sort of use the previous stuff we have had and learn as econometric methods to overcome those challenges.